Hello everyone. In this video, we're going to be looking at how we can use S-Frame and its meshing capabilities to observe local buckling behavior in different beam systems. Now in this example, I've actually converted a member which had a cross-section assigned to it to a meshable panel, or a series of meshable panels. Now this process is discussed in other videos, which I'll link to here. But in this example, we're going to go through the process of basically running an analysis where we have a point load, we have fixed supports on either end, and we want to observe the behavior of the model under these loading conditions. And we're going to be looking at nonlinear behavior to capture the buckling in the local elements. For the purposes of this example, we have very thin flanges on this I-beam section, 5 millimeters, with the intention that we are going to induce some local buckling there. So with that here, let's just introduce the model a little bit more. You can see how we have a variety of meshable panels with different thicknesses that were automatically created based off of conversion from an existing member. And I've got a single load that's applied mid-span here, 10 kilonewton load. And we're actually going to scale this up with the intention that we can evaluate it as it starts to approach the buckling limits of our elements. Now we're going to mesh this model. And I can do that already just by clicking on the mesh panel elements of type membrane, plate, or shell. And it's going to generate a mesh for me, which I'm satisfied with here. And the advantage of using shell elements to model these, this type of structure is that we can actually study now the local effects of items like buckling and other behaviors that we couldn't represent accurately with a member model, which only has a single line and perhaps different joints along its length to represent the entire cross-section. So I'm going to go ahead and run the analysis here. Again, we've already examined the loads, so I'm just going to run a nonlinear static analysis. Some of you may be wondering why I'm not running a buckling analysis. Well, I could run a buckling analysis, and that would give me some reasonable results to give me a somewhat accurate view of the buckling behavior. But the most realistic method for this type of analysis is actually a nonlinear static analysis. And what I've done is I've actually increased the number of load increments to 100. The default is 10. So I'm scaling up the magnitude of my loads with the intention that I will have a load that causes buckling. And I'm going to break down that load vector into 100 different even increments that are applied incrementally. And these are being solved incrementally, and I'm including those increments in the results so that I can actually look at the lead up to the failure, which will be very important for me. So click OK to run the analysis. And I'm brought to the graphical results window here, and I can see under the load case view, I have my main parent load case, underneath that a number of different step load cases. These are all the different increments. So I can look at basically the incremental results that lead up to this type of failure. And this can be very useful to study the behavior in more detail. I might want to look at, for example, at any point along my flange here, I can right click on a joint and I can say, let's look at incremental results. And under the incremental results table here, I can look at basically the deformation against a load increment plot in different directions. So I see the x-axis, I see the y-axis, and I can see the z-axis. And what's interesting to us here, and the y-axis is the one that I'm most interested in at the moment, is that we can see that it was somewhat linear with some deviations here, but then all of a sudden it goes to be quite nonlinear. And it is a bit subjective how we quantify or characterize buckling, but we do notice with a relatively small change in the amount of load that we applied, going around, let's say, load increment 70 to load increment 80, we have a fairly major jump in the deformations. So for my example here, I'm going to characterize that as buckling. And we can also look at the results in SView as well. So I can go to Run and SView and launch SView. And here under SView, I can change to a different display if I'm interested in, but I can see the rendering of my section. And I can look at the deformation for each load increment, and this can show me a lot of useful data. So here I can see that the model is definitely deforming, and then if we look closely, we can see a lot of deformation, which has been exaggerated, but we can see deformation in particularly the top flange here, but also the bottom flange on this side as well. So we could characterize that as local buckling in this particular model. And that would be very difficult to characterize and to represent with just a one-dimensional element. Now we also have ways of combating that local buckling. We could use stiffeners, for example, within our webs between the flanges. And I have a model that's already constructed with that. So let me just switch to that model. And this is the model before meshing, where we have basically a number of additional panels that have been added to our I-beam panel arrangement. And there are actually automated ways to help create these panels for us. That will be the topic of another video. But what I do want to mention here is that once we mesh this, and I have meshed and analyzed this, just to quickly jump into that model. With everything the same except for the addition of those stiffeners, we can look at the graphical results. And here I can zoom in on an approximately similar location here. Let me just do somewhere away from one of the stiffeners near the center of this flange, and I'll look at the incremental results. And here I can see in the X direction, the deformation, which wasn't really that nonlinear before. I can see the Y direction as well, and I am getting some more jumps in the deformation, but it's further on in the loading and less severe, and in the Z direction as well. So we can see that these clearly did have a positive effect on the local buckling. And of course I can view the deformations again in S view and better understand how that's behaving on a global scale. So I'm just going to switch to my favorite object view here, and I can zoom in and display the deformations. And we can see as we get towards the end, we're not getting that same flange buckling effect that we had before. Now, if you'd like more information about meshing or about steel design or anything to that effect, please check out our other YouTube videos or visit Altair 1 for more training information.